thing going. Okay. All right. So we are going to be looking at quadratic functions. The good news is these are things that we already know a fair amount of stuff about. Just about any time you see the word quad show up in a math context, it's referring to a square. So we're just looking at functions that come from or are related to y equals x squared. Okay, so quadratics come from y equals x squared. We are familiar at least with the basic function then, y equals x squared, right? Passes through the origin. Sorry. Its domain is the whole real line. Its range is, well, you tell me. 0 to infinity, and 0 is included. This one's opening up, right? So the range, this point at the origin is the lowest point on the graph. A little bit of new terminology stuff. That point's called the vertex. Let me draw this somewhere here. The shape of the graph is called a parabola. I've probably been using that word some, but now it's official. So the graph for a square function is a parabola, that point that we've been keeping track of anyway, right? Because it's visually distinct. I can tell it apart from the others. That's called the vertex. One other like terminology thing. The vertical line that runs down the middle of this. So when we talked about even functions, right? We used x squared as an example because it's even, it's y-axis symmetric. If we shift it away from the origin, then it's not even anymore, but still has some kind of self-reflexive like symmetry stuff going on. This line that runs down the middle is called the axis of symmetry. So for this one in particular, the vertex is 0, 0. And the axis of symmetry then is the vertical line that runs through 0, 0, which we would write as x equals 0. And again, that's because that's a vertical line. Okay, so again, just a little bit of terminology stuff, right? Nothing really new, just putting names on things that we've already been looking at. For the most part, if we know these things, and in particular the vertex, along with whether the function, the graph opens up or down, right? Which would be based on if that square term is positive or negative. If it opens up, then the vertex is the minimum value. It's the smallest the function ever gets. That means the range is from whatever that y value is up to positive infinity, right? On the other hand, if it opens down, then the vertex is the maximum value. The range would be like negative infinity up to wherever that is. But in a lot of applications, finding the minimum or finding the maximum is going to be the thing that we care about, right? So a lot of the problems that we're going to do for the next couple of weeks are going to be optimization problems where I've got some function that models, I don't know, like profit, right? Like I'm running a shop. I've got this function that models profit. Well, the thing I care about finding and trying to achieve is the maximum where that profit occurs, right? Which is going to end up being the vertex. So a lot of what we're going to talk about is going to come down to, being able to identify that vertex point and find that. Okay, let's look at an example or another example, I guess. Say f of x is -2, x plus 3 squared minus 1. What do we know about that? Using, again, stuff we already knew coming into today, right? We've got new terminology now, but what can you tell me about the graph of this thing? It's a square function that's got a reflection over the x-axis. The 2 is a stretch thing, right? That changes the shape, so it's taller and skinnier than x squared would be. What else? Yeah. And down 1. Okay. Again, that's stuff we already knew, right? That's just transformations. Here's what happens. What's the vertex then? -3, -1. Yeah. And because of that x-axis reflection, it opens down, right? So whatever else happens, I know that, sort of big picture terms, this looks like this. It's opening down. Again, the stretching thing means it's going to be kind of taller or skinnier than a normal x squared would be, but whatever. I probably don't care that much about that unless I'm going to get really into the details. And the vertex is at -3, -1. Well, that's the tallest point. That's the maximum value of the graph. What's the axis of symmetry? It's the vertical line that goes through the vertex. So -3, because it's a vertical line, the equation for it would be x equals -3. Just watch out for that. Okay, and I get the domain and range too then, right? The domain, it's a quadratic. Those are defined everywhere. But the range, it's opening down. So -3, -1 is the top. So the range will be right idea, backwards, -infinity to -1, right? So reading, sort of like, think of the way it's oriented on the y-axis. We want to read like bottom to top, right? So it stops at -1. Yeah, good. Okay. And again, apart from the fact that I gave you like 2 new words, nothing new there really, right? Okay. This sorry, right with that. This is what's called the vertex form for a quadratic function. It's called the vertex form because I can look at it and I can read off where the vertex is, right? I can look at that. I know my transformation stuff. I can see, okay, well, I went from 0, 0 to the left 3, that's -3, down 1, that's -1. So -3, -1 is the vertex. It's just sitting right there, right? The vertex form. Now, again, this is one of those things where, if I put it in the sort of formal math speak language of a textbook or whatever, it looks like that, which makes it look a little more complicated, but it's the same thing, right? A times x minus h squared plus k. Coordinates of the vertex are hk. Well, again, that's h is shifting to the right or to the left. K is shifting up or down. It's just transformations. That's great. That's the thing that's going to be kind of most familiar to us right now, because again, it's not really a new thing. We're just putting a new name on it. There's one other sort of common way that we'll see quadratics, and that's this standard form thing just above it. Standard form looks like this. Standard form, f of x is ax squared plus bx plus c. So everything just sort of expanded, like terms combined, just, descending order of the powers. You got the square term, the linear term, and then the constant term. The vertex form thing is great because it tells me about the vertex, but it's a little bit clunky if I want to, work with it or solve an equation or something like that. Standard form is a little bit cleaner to write down and a little bit better for working with in a lot of contexts. So that's why we have kind of two things that we'll go back and forth between. The way you get from one to the other if I have the vertex form and I want the standard form, all I need to do is start expanding things and basically simplify everything down. So what's x plus 3 squared?
X squared plus 3x is 9.
X squared plus 3x twice plus 9, right? FOIL or distribute everything, however you want to say that. Put it in the wrong place. And then combine like terms. Okay, so that's x squared plus 6x plus 9. If I distribute, then this becomes negative 2x squared minus 12x minus 18 minus 1. That's the same function, but written in standard form, right? A is negative 2, B is negative 12, C is negative 19. Again, that's just the coefficients. So that's the same function in standard form. Standard form, again, I can't look at and read the vertex off anymore. So, I lose that. I can't tell just by looking at this that the vertex is negative 3, negative 1, but it's the same function. I can still tell that it opens down because of this, right? The square term is negative. If that leading term is negative, that forces the whole thing to open down. So this still opens down. I have to do a little more work to find the vertex. To find the vertex for a thing that's in standard form like that, get the x coordinate by taking the opposite of b divided by 2a. This is a thing that I can't really, justify why it's that without, because we need calculus to like show where this thing comes from. So we'll just take this as kind of a given, formula if you want. Negative b over 2a, that gives you the x coordinate for the vertex. What's b here? Negative 12. And a is negative 2. So the opposite of negative 12 divided by negative 4. So the opposite of 3, right? Negative 3 is the x coordinate for the vertex. Then to get the y, you just plug that back in. What was it? Negative 1. Again, finding the vertex is going to be pretty common thing that we'll need to do in applications and in different places. It's important because it's the maximum or the minimum value. So we want to be able to do that, kind of quickly, efficiently, easily, whatever. That's the way to get it for a thing that's in standard form, the negative b over 2a. Okay. The other direction, so that's going from vertex to standard. Vertex to standard, again, we're basically just following the directions that are already there, right? Like square this thing. Okay, I squared the thing. Multiply by -2. Okay, I distribute the -2. I combine like terms. That's pretty much it. This direction shouldn't feel like too big a deal then. Going the other direction is a little bit more involved, a little bit more complicated. So let's take a look at on the notes the first two examples there, 1 and 2. 1, I gave you a function that's in the like vertex, the written out transformation version form, right? I want you to find the vertex, the axis of symmetry, the domain, the range, and then rewrite it in standard form like we just did, right? Number 2, that one's in standard form, right? X squared plus 6x plus 8. I want you to find the vertex. That's going to be using the negative b over 2a thing. Once you have the vertex, you get the axis of symmetry for free, basically. Domain, you know, the range, you basically get that for free from the axis or from the vertex as well, and thinking about which direction it opens. And then rewriting in vertex form by completing the square we'll need to talk about. But take a minute and try to find the vertex and stuff for those. Mm-hmm. Okay, so for one, we've got this sort of perfect square term in there. We've got, stuff on the inside and the outside. This is the vertex or the like transformation form. So I should be able to look at it and pretty much know right away two things. One, which direction it opens, and two, where the vertex is, right? So which way does this open? Down. That negative sign out in front of the whole thing, if I'm thinking transformations, that's an x-axis reflection. What that means is that the thing is opening downward. So the vertex, whatever it is going to be the maximum value. The range is going to be negative infinity to something, right? I know all this just from that negative sign parked out in front. What is the vertex? Two, -3. 2 to the right, 3 down. Okay. The axis of symmetry then, again, I get for free along with the vertex. It's the vertical line through x equals 2. So the equation of it is x equals 2, right? Because it's a vertical line. Domain, quadratics are always defined everywhere. So like the whole real line. The range, yep, negative infinity to -3 because it's opening down. All right, good. Rewriting in standard form, expand everything, carry the negative, distribute like terms, whatever, all that stuff. What do you get? Yep. Good. Okay. And again, there, that part I need to do a little bit of algebra to find. Everything else is pretty much just sitting there, right? It's just about, making sure we know how to read it. 2, we have to do a little bit of work to find the vertex, right? It's in standard form, so I don't have it just sitting there where I can kind of read the transformations off. But to find the vertex, x is negative b over 2a. B is 6 and a is 1. So that's -3. And then if I plug that back in, -9 minus 18, -1, -1, -1 maybe? I don't know. Somebody check that, but okay, cool. What do you use? We'll fig- Okay. Okay. We'll look at it. Okay, axis of symmetry then is negative, x equals -3. Which way does this thing open? Up. Because that leading term is positive, it opens up. And the range then would be -1 to positive infinity, right? Opening upward. Okay, so that's all of the, vital stat stuff. Like now I have a pretty good idea what this looks like. I know where it is. I know it opens up. I've got its domain and range. Rewriting this in vertex form by completing the square. I've italicized completing the square, you may notice. Completing the square is, you can think of that like a proper noun if you want. Like that's a specific technique that we're going to use to get from something that looks like this to something that looks like that, right? That's the idea. We're trying to basically, a minute ago when we expanded this whole thing, completing the square is the way to work like bottom to top there. Okay, so what was it? X squared plus 6x plus 8. All right. The way completing the square works is that we want to do some stuff and end up with something that looks like this, basically, right? A perfect square, factored term with maybe some stuff left over on the outside. We know the vertex here, right? It was -3, -1. So I actually know the answer, right? I'm working toward this. But a thing that looks like this is our goal. right? To end up with a perfect square. So the name completing the square part is that I want to end up with a factored perfect square. The thing I have to do is complete it. If we have to complete it, that means it must not be complete already, right? Okay, so we've got a thing that if I want to look at it as a perfect square is missing some stuff, right? It's somehow deficient. We got to figure out what's missing and then, fix it. Okay, so look at how we went the other way, because we're basically trying to reverse this process, right? X plus 3 squared means multiply two of them together. Multiply two of them together means distribute everything, FOIL, expand, however you want to say that. I get this. And then we, sometimes without really even thinking about it too much, combine those middle terms because they're the same, right? They're like terms, combine those into one thing. Well, to work backwards, we have to make a little bit of a leap, and that where that happens is right here. This is the way into the problem. Take that middle term. If it came from a perfect square, that means it came from two identical things. That means that these two are the same. So if I take that middle term and break it in half, divide it by 2. Oh man, I mean to do this with the same numbers. Can I change that 6 to, I don't know, an 8? I know it won't be the problem that's, in the notes. Oh, fine, we'll do it with the 6. Okay, whatever. We'll just move on. Okay, so look at this. Divided into 2 equal pieces. If I split positive 6x in half, what do we get? (3x) twice, right? Okay. Completing the square, this is it's a thing that's very much going to feel like a trick the first time, but then you do it again and we call it a technique instead, right? But it's a thing that we do because it works. So I take that middle term and break it in half, split it into 2 equal pieces, right? Because that's where it came from if I was working the other way. So I have x squared plus 3x plus 3x. I'm going to make a little room here. Because if what I'm doing is trying to fill in the missing piece of this square, that's where I'm going to put it. The way I want to think of the stuff that we have is treat those as though they came from expanding a product of binomials, right? So if I multiplied 2 terms and got x squared plus 3x plus 3x as the first and outer and inner parts of the product, right? So the FOI is x squared plus 3x plus 3x. Then what must the factors have looked like? If I multiply these 2 things and get x squared, what goes here and here? X in both of them, right? Because x times x is x squared. Okay. Well, if the outer part of the product, so this times this, is 3x, I have the x, right? What's the other part? Plus 3. If the inner part of the product is plus 3x, well, I've got the x again. Well, it goes here. 3 again. Multiply this out. X squared plus 3x, check, check, plus 3x. But then there's another thing. Plus, 3 times 3, 9. That's the missing part, right? That's that my square was incomplete because I don't have that plus 9 there. Well, I'd really like to have a +9, so let's add one. Let's put a +9 there. Because multiplying this out gives me that. Okay, but what's the problem now? Like I just invented that +9 out of nowhere, right? Like the +9 wasn't there. I need it to be there so that I can factor. That's the completing the square part. We've completed the square now. But I've changed things. I said that these were equal and these were equal, but all of a sudden that's not true anymore right here. Right? Because I've conjured up a +9. So how do we fix it?
Minus 1 on the outside of the.
Yeah.
X plus 3.
You added 9, so take it away also. What's 9 minus 9? 0. You're always allowed to add 0. You're always allowed to add 0. You're always allowed to multiply by 1, right? We use that when we work with fractions. I'm adding 0. Well, okay, adding 0 doesn't change anything, right? It seems like a stupid thing to do. Like I wouldn't just write +0, but if I write it as +9 minus 9, it's useful because this 9 is in here now, right? It's in this factor thing. And left over on the outside is the -1, right? Because I combined those terms, 8 minus 9. And finally, this is x plus 3 squared, because there's 2 of them, minus 1. That's the same thing in the vertex form. Like I said, that direction is more involved, right? Because we're not just sort of following the directions that are already there, that are already laid out for us, like we are going this way, or working bottom to top. But we're doing all the same things in reverse order. So the way we get into it again is taking that middle term and breaking it into 2 equal pieces, dividing it in half. I divide that in half. That shows me what the factors need to look like. That tells me what's missing. And then I can, sort of correct that, right? Adjust for it. Okay. This is a thing that like you're just going to have to do on your own a few times before it, really starts to sink in or click. Obviously you get to do that with homework, but give it a shot, tonight, go to the homework and find a couple where you can do this or do whatever's in the notes. And then if we need to talk about it some more tomorrow, we can. Does anybody have any questions right now though about like where anything came from or how anything happened there? Okay. Like I said, we'll come back to it tomorrow and talk about it some more if we need to after you've done like a couple on your own. But watching me, do them all day isn't going to help you any more than doing one. Okay. So that's, how I would answer this, right? For 3, you're going to do all the same things. I'm going to leave that one for you to do tonight. For the last part, the completing the square, just a nudge in the right direction. All of the coefficients there, 2, 4, and 16, those are all even. So start by factoring that 2 out and then just work on this part, right? Like the 2 is going to sort of stay kind of parked outside like that because that's a stretching thing, right? That's making this parabola sort of more narrow. Yeah.
Isn't it a -16?
Oh, yeah, sorry. Yeah. But basically ignore that 2 as much as you can for the purposes of doing the completing the square stuff. Because if you think about it, that 2x squared, if you try to break it up into, think of that as the first part of the product. Well, x and x, but like, how do I deal with the coefficient, right? So instead, just hold the 2 to the outside like that instead of trying to factor it.
The final product of what you get right there, you're gonna have to factor it.
Yeah. So you're going to actually do, the completing the square part on this.
Okay.
Yeah.
And that's.
Okay, so that's my, shove in the right direction on that. Flip over to the back and let's talk about, some places where we use this. 4 is very similar to, well, actually very similar to a question that was actually on the test, but same kind of deal. You should be able to handle that just fine. The vertex form, pretty much you want to just think transformations and kind of write down, then the standard form, just do the algebra to find it. Take a look at 5 though, read through that a couple of times, get your head around what's going on there. Okay, so what are we looking at? Yes. Go Chuck McFootball, throwing footballs. He was born to play the game. This function, which has, weird, unpleasant coefficients, 0.02, whatever, but it's quadratic. It's in standard form. What are A, B, and C? Yep. B is 1.2. C is 6.3. Which way is it open? We're looking at something like that then, right? One of the important applications of quadratics is in modeling projectile motion. So if we ignore, wind or whatever, air resistance, then the path that an object throws, if it's, acting under gravity, you throw it up in the air, it comes back down, follows a parabolic arc, right? So the shape of this is a parabola. That means I can model it with a quadratic. Here's the quadratic that models this one. The height of the ball in feet can be modeled by, that means the y value is height in feet. This function where x is the ball's horizontal distance in feet basically that just means that, it's like I'm watching from the sideline and, x is how far downfield he's throwing the ball, basically, right? You can do the same thing, modeling the height as a function of time. You'll see those as well, where it's written in terms of t, and t is time in seconds or whatever that it's been in the air. So this function looks like this if I look at it in just a standard, 10 by 10 graphing window. If I zoom out a little bit so that I can see kind of the whole thing. Again, I see a parabolic arc. It goes up, it comes back down, and then at some point here, this would be like hitting the ground, right? So I don't really care about anything beyond that point. Since it's opening down, the vertex would be the maximum, right? Look at what we need to find. The maximum height of the ball, how far the ball traveled when it reached the maximum height, and from what height did he throw the ball? Well, I know how to find the vertex. What's the vertex tell us here? Height was, let's be more specific. At the highest point, right? Vertex, though, is an ordered pair. It's got an X and a Y coordinate. Which of those is the maximum height? Like, how do I answer part A? Yeah. This would be the Y coordinate of the vertex. What does the X coordinate of the vertex tell us? How far it traveled before it got there, right? So the XY here of the vertex, that's how far it traveled before it got to that maximum height. This is the maximum height. How do we find the vertex? I can either do the whole completing the square thing to get it into the vertex form. What is? Oh. I can either do the whole completing the square thing to get it into the like vertex form so I can read it off. But those coefficients are messy and decimals and like that's gonna be a whole thing, right? Or negative b over 2a. B is 1.2, A is negative 0.02. Make sure to be careful, it's the coefficient only, but the sign goes along with it if it's negative. So somebody tell me what that is. $30. Negatives are going to cancel, and just make sure that you do, 1.2 divided by 2 times 0.02, right? This multiplication needs to happen first. Okay, so 30. How far had the ball traveled? 30 feet. Maximum height of the ball, plug in 30. Whatever that is. Okay, what about part C? From what height did he throw the ball? Where do I need to look to find that? 6.3. Okay, why? Because. Okay. It's the y-intercept. Why is that the y-intercept? Yeah, if you plug in 0, these terms drop out, and I just get 6.3. So that's another, in the like pros column for the like standard form thing is that I can read off the y-intercept. I can't read off the y-intercept in the other one, the vertex form. Y-intercept 6.3. Why would the y-intercept be the height that he threw the ball from here? Okay. It's in the way that the function's set up. What are y values here? Just like in general. Height. And x values are distance, but we start counting the distance like where he's standing, right? So where he threw the ball, that's when the ball, like the moment it's leaving his hand, that's when the distance between him and the ball is 0, right? So that's why it's the y-intercept. I want to plug in 0. Anytime we're talking about an initial value, a starting height of whatever, it's probably going to be referring to the y-intercept. So if it's in terms of time, I'm starting the clock at t equals 0 at the moment he lets go of the ball, right? Here it's distance. Okay, well, I'm measuring that from where he's standing. So that's when x is 0. When x is 0, we're talking about the y-intercept. If I plug in 0, I get just that c term, 6.3. And that's a number that makes sense as a height for a guy to be throwing the ball, right? So there you go. Okay, so finish those. Do the ones that we skipped, 3 and 4. We'll talk about Farmer Ed and his barns tomorrow. All right. So do some homework stuff in 3.2. Try the completing the square thing a couple of times to get a feel for it. And if we need to hit that tomorrow, we can do that as well. Y'all have a good day. I'll see you then.
Good day.
Thank you, you too.
That's great.
No.
What's tomorrow?
There's a chance it'll be tomorrow. It's looking more like Thursday, probably. But,
Okay.
yep.